Afternoon, ma'am.
Hi, how are you?
Not too bad. Struggling
Good.
on the homework a little.
Yeah, no, I know. I'm gonna solve some problems today. Usually the first homework on transmission lines is always tough because people are trying to remember things. And so what I have done, in addition to today, I'm recording this session. So I'm gonna start solving some problems similar to the homework. And then also I have uploaded. So for the first two problems of the homework, I have uploaded slides and a video from the problem solving session that you can. Did you look into that? Did you by any chance have the ability or the time to look into it?
Yes, ma'am. Actually, I was in that session as
Oh, you
well.
were in the session. Okay.
I had to leave early
So,
because I had somebody come to my house,
oh,
but
that's okay. No, I
we got
understand
those
that.
two problems solved.
Okay, perfect. So today we're gonna do Smith chart. And I will upload those two. So it's going to be also a review, and then we'll solve a problem similar to what we have in the class.
Okay,
So
and I
you're
have
going to
another question on that
Go
as
ahead.
well.
Mm-hmm.
If
Okay.
you're going to upload the video and the slides for that, is there any chance we could get our homework assignment due at the end of Monday evening, since the day off as well?
That is true. That's a good, I have no problem myself. I will do this for everybody.
That would be amazing. It just kind of occurred to me because I know it takes you a day just to upload the video, and then that's kind of crunching it to get.
No, that I understand. Yeah. So in fact, some videos, I have to tell you, I was looking at another video, and I don't know what it is with the internet. In the video you're going to see for the first problem, the first part of it before we started on the Smith chart was really good. The other one was like on and off for some reason. In any case, we're gonna, yes, I will upload this, but also I think some people have families, may visit their families and stuff because of Labor Day, and so I will extend it to Monday.
Thank you very much, ma'am.
Sure, no problem. Okay, I think I'm gonna start. And then people can join us as they wish. So let me see. What I was looking into doing, it was sharing.
There's three of us with me that have been working on the homework together. So there's two other classmates in here with me.
Oh, okay, perfect. Okay, now I have to find out where I'm going for sharing. Let me see. Share. Okay, I got it. Screen. There. In fact, I have my family at home and I have my granddaughter here. So if you hear anybody screaming, don't get upset.
I got my own daughter. This is my weekend. She's at her mom, so
okay. Well, yeah. Well, sometimes we have that when they visit. In any case, so what I will do today, I have decided. Okay. I will cover some things like rules you need to remember, and then I'm going to use the Smith chart to remind you some other things probably you have seen in the past, and then we're going to start solving a problem. So first of all, of course, we use the Smith chart to show impedances and admittances, all right? And make sure, if you see, by the way, let me make a comment that if you see the recording, is it recording right now? Probably.
Yes, ma'am.
Yes, okay, perfect. If you see it going off, let me know, because they will have to restart. Sometimes it happens. Okay, so we use the Smith chart to show, to solve transmission line problems. And it's a very intuitive, eventually becomes, when people get used to it, and very easy way to do some very complex calculations. And people developed the Smith chart before the First World War. And then it was so good in terms of designs that were able to design very complicated radars and receivers without computers. So in any case, I want to tell you how that's why it has really survived it for so many years as a tool. And now, of course, paper is what we use, but in many instruments we are using for diagnostics and ADS also, you will see that they have an electronic Smith chart because it gives you ideas how things go, move in terms of frequency. I mean, it has an amazing amount of information that you can provide. So even if we got computers, the Smith chart remains. So the Smith chart is used to show impedances or admittances, and admittance is the inverse of an impedance, obviously. And it's used to show complex impedances, all right? Then all impedances, real or complex or imaginary, are measured in ohms, and admittances, which are also complex in general, are measured in 1/ohm, which is a Siemens. So we will use the Smith chart. The first thing we will do is to identify where those impedances are. And then also we will use the Smith chart to go from an impedance to an admittance, which is easy without having to make an inversion of a complex number. Okay, so rule number 1, you cannot use the Smith chart without normalizing the impedances or admittances. They have to be normalized. Ideally, in easy problems, all of the transmission lines involved have the same characteristic impedance. So we always use that characteristic impedance for normalization. However, that's not always true, as you will see from the problems. Sometimes the characteristic impedances are different, and sometimes one of them is an unknown. So to be able to solve one problem on a Smith chart, we need to normalize all of the Z's, the impedances with the same characteristic impedance or reference impedance, how we call it, and all the admittances with the same reference admittance. So if we are on one Smith chart for one problem, then usually the characteristic impedance or the reference impedance, so reference impedance here is 1/the reference admittance. Is always a real number. And if it's not specified, we always assume that it's 50 ohms, if not specified, unless specified differently. Okay, so in rule number 3 says that to normalize an impedance, you need to consider the characteristic impedance that has been provided in the problem. Usually, in most problems, characteristic impedances are in 50 ohms with exceptions, and we will see that. So let's, for example, take an impedance here. Okay, let's consider an impedance Z here, which is complex, has a real part, 80 plus J, 50 ohms. Okay. And we have been given a characteristic impedance, which is Z0 here. Do this, Z0. So now we normalize Z, and we always indicate the normalized impedance with a bar. And when we normalize it, it becomes this one, Z equals this ratio, which in fact gives 1.6 plus J1. And normalized impedances have no units because obviously we divide ohms with ohms, so the units go away, so no units. They are numbers. Okay, so rule number 4, I repeat exactly. If a characteristic impedance has not been specified, then you're not, but they give you Z0, for example, somewhere without, however, a specification, you assume that this Z0 is 50 ohms and you use that to normalize things, all right? So if Z0 has not been specified, then you assume, here, let me write it complete in you assume let me remove that. You assume that Z naught is 50 ohms, and you use this to normalize. Use it to normalize. Okay, so that is rule number 4. Rule number 5. Whenever possible, you use the Smith chart exclusively for impedances. You work exclusively with impedances or exclusively with admittances. Unless you are very experienced, you should not go from one to another if you can, all right, unless it's required somehow. But most of the time, you will assume now in our problems that we are going to use either impedances or admittances, because usually going from one to another can be very confusing for early users of the Smith chart. I said, however, before you use the Smith chart, you will have to normalize all impedances with respect to Z naught and all admittances with respect, when you use admittances, with respect to Y naught, which is 1 over Z naught. So normalization should never be forgotten. Okay, now we will apply these rules and we will find the 3 impedances that I gave in the beginning, and we normalize them with respect to 50 ohms. All right, they have not told us how to normalize them. They say use the Smith chart to find them, and we use 50 ohms. And then Z1 normalized becomes 0.6 plus J3, Z2 becomes 1 plus J minus J1.6, and Z3 becomes 1.2. Okay, so then we take the Smith chart. All right, so what we do, how we find the impedances, first of all, we need to remember. All of these are reviews, all right, whatever I say right now. And then what the other thing I want to suggest is that not only use my notes, but if you have your own notes from previous classes, revisit those, because you have studied obviously these notes and it will be a lot more familiar to you. Okay, so first of all, we look at Z1. Z1 has a real part 0.6 here, imaginary part 3. So 0.6, we go along the horizontal axis, which this is this one. All right, I will erase it all because then we cannot see the numbers. And we find 0.6, which is right where I have this dot. Oops, this dot here. All right, then we go and write this red circle. What is specific about this circle? Its center is somewhere on the real axis, this axis that I showed before, and is tangential to the Smith chart right at this point, right here. Let me do this here. So all of this red, always I will use a red circle, and the yellow, for example, they all are tangential here at that point. Okay, so I have 0.6. Then we know that the imaginary part is J3. So then I go in this perimeter of the Smith chart, which starts here and goes all around. And at this point starts at 0. And the upper hemisphere is positive, the lower is negative. And the upper, it goes from 0 here to infinity here. So 0 in impedance is short circuit. Infinity is open circuit and has all the values in between. On the upper side of the circle is positive values, inductive. On the lower side is negative values, capacitive. So I read along this circle, and then you see the numbers underneath it here. The numbers are here, right? 1 is here, 1.2, 1.4, and then find 3, which is at this point. Okay, Now let me erase those things. Don't need them. And then what do? Then I draw the line, which is part of a bigger circle. Most of it lies outside of the Smith chart. But I have the line, and then I go and I draw. And this line, the green one, is not very correct the way I did it. So practically, if I draw it, and I will do it for you here, it's gonna go, if I'm careful, it's gonna go like this. In fact, I don't have to be very accurate down here, but I have to be accurate at this point where the intersection with the red circle, all right, that point here that you see is giving me that intersection where belongs to the red circle and to the green is the normalized impedance Z1, all right? And it has real part 0.6 and imaginary part 3. So in fact, here I could say 0.6 plus J3. All right. Now, let's go to Z2. Z2 has a real part of 1 and an imaginary part of minus 1.6. So 1. 1 is here. All right. And therefore, we write this other circle, which is like lighter red, this one. And it goes around like the first circle, has the center on the horizontal line, and then also is tangential at this point. And then after I draw the circle, I go and find, since the negative part of this is minus 1/6, I go underneath here, under, all right, in the lower perimeter, and I find 1.6 here. And because it's in the lower part of the circle, it's negative. And therefore, after I do that, I draw the green circle that is like the previous one, but it starts at 1.6 and goes all the way up like this one. It goes all the way up, all right, along this line, like this. And then I see where this circle intersects with the red one. And even if, you know, these dots are not actually very precise, you will see that then eventually the solutions are precise down to the third decimal point because of how that has been developed, the Smith chart. So then the intersection of the light red circle and the green one is Z2, which is, as we said, 1 minus J 1.6. And then the last thing is we need to find Z3, which is 1.2, and it's only real. And 1.2 is here. I have found it. I draw the yellow circle, but it does not have an imaginary part. So practically the point is exactly 1.2. All of the points of the yellow circle, all of the points have the same real part, but the one that is on the real axis is the one that has 0 imaginary. All of the points on the real axis, which is this, that's what I call the real axis. All of these points have 0 imaginary part as normalized impedances. So that's how we use it to find an impedance. Now, to find the admittances that correspond. So the next thing is, I could ask you to find the admittances Y1, which is 1 over Z1, Y2, which is over 1 over Z2, and Y3, which is 1 over Z3, Okay, we're gonna find their admittances. Now, how do I do this? To find the admittance, after I have solved for these impedances, so for example, I will go down to another, I will add another Smith chart, so I don't erase this one. A page, and then I will take this, okay, copy, and then go here, paste. Okay, but I will erase this thing. I will leave only the points, but I will erase this. I will erase this, and this, all right? And this. Okay, these are the 3 points that I have found, the impedances, and I want to find the admittances for all of them. Now, what I do is I draw from each point. Let's start with Z1. I draw at each point the circle that connects, has the center, its center, and let me give it a, what color, give it a purple. I will draw the circle that has the center of the Smith chart, and then goes through Z1. So I will draw a circle like this, and then I will fix it. Okay, so see, I hope this is the right one. Okay, maybe it needs to go a little further here. Yeah, all right, and then I draw a line from, let me draw the line with this one. I'm drawing a line from this point through the center until it meets the other side of the circle, all right? So I'm drawing the diagonal. Let me see. Or the diameter, but diagonal is for square. Diameter. Okay, anyways, cannot do that for time being. So you go to the other point down here, and then you look at that point. In fact, I think, oh yeah, correct. And that is Y1 normalized. So it's the inverse. So I can write it here. Is to find exactly what is the value for this, we have to find its real part. So we have to draw a circle. And in fact, the circle, the way it is so close to this side. So let me see. The circle goes like here. No, that's not the right circle. Sorry. It's going to be somehow close to this one, I think, because it's so big. So it's the circle that will go, let me see, the resistive part. Something like that, and fix it. Yeah. All right, so it's gonna go a little further in. All right. This one, if I were to measure, oops. Oh, okay. If I were to measure that here, okay. So this is gonna be 0 at that point. And then this point 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So here is 1, 2, 3, 4, 5, 6, 7, 8, 8.5. So in fact, 0.085. So this red circle, all right, so this is going to give a point 0.085. That's the real part. Imaginary. To find the imaginary part, then we have to draw a green from this all the way like that. And we have to read here what number that is on the innermost perimetry of the circle. So here we have 0, here we have 0.1, here we have 0.2, this is 0.3, and probably is 0.32. Okay, so let's write here that this is, and because it's below, is minus J.32. So practically, let me write it here, what we found. We'll do it for one, and then you can do for the others. Y1 normalized is 0.085 minus J.32. Okay, now, if this is correct, that practically the inverse of that, I can prove that this is correct if this one gives me 1 over Z1 normalized, or if Z1 normalized is equal to 1 over Y1 normalized, okay? And then I can prove that. So Z1 normalized is going to be 1 over 0.085 minus J.32. And then to make the denominator real, I multiply by its complex conjugate. So it becomes 0.085 plus J.32. And then I have 0.085 squared plus 0.32 squared. And let's see what that gives. Okay, 0.085 square that gives 0.0072 plus 0.32 0.1024, which practically, if you had a calculator that does all of this, will help you, which I don't at this point, 0.32. And then it has 6, 9, 0, 1. And then let's see what that gives. 0.085 divided by 0.1096. How much it gives? It gives, I was not as good in counting that. It was 32.085. Okay, so let me do this again. 0.085 divided by 0.1096. It gives me 0.77 instead of giving me 0.6. So most probably I have not been very accurate in this one, which means that the resistance should have been, okay, my circle is not very good. My guess is my circle, this one, I did not draw it very carefully, so the center is not there. But in any case, let me approximately, all right, because I did approximate things. So that's going to be what I get is about 0.7 here. And then plus J, let me see the other one, what it gets. The other one is not even, I don't know why it gave me this.
Ma'am, the real portion for the white one, I got a little bit lower. I got 0.06, I believe, or 0.6.
Okay, maybe that's better.
0.06 is what I got.
Okay.
But the
Instead of
Z1,
0.08,
your Z1,
okay,
that's supposed to be 0.6 plus J3, correct?
plus J3, exactly.
Okay.
Yes, perfect. All right. Maybe that's close. We'll see. The other one is 0.32 divided by 0.1096. The other goes J3. So I was somehow, anyways, the way I did my circle, it was not accurate. So the real part, when I measured it, was not correct. Did not give me the correct real part, but it's close enough. Anyways, you get the idea. If you can do the circle, if you can do it correctly with the center, and then on ADS, you're gonna be able to do that, So by hand, for example, you need to have a compass to do it, as opposed to what I do here without a compass. But in any case, it gives you, all right, it gives you exactly that. And this is approximately, I would say, so approximately, this is close to 0.6 plus J3. So if you do it correctly, it's gonna be identical, the same. So in order to go from an impedance to an admittance, you just have to draw, and the reverse, you have to draw the circle that connects either one and has a center, the center of the Smith chart, and then you draw the diameter. And then you find the diametrically opposite point. And if you started with an impedance, that will be your normalized admittance, and the reverse. So that's how we remember how to get it, admittances and impedances on the Smith chart. Any questions about this? These are fundamental steps. Now, the next thing that I would like to do is to find out how we move an impedance on a Smith chart. All right, and here I gave an eighth of a wavelength, but then I will show you a quarter of a wavelength and half a wavelength, what they do. Okay. So now we have a generator. Generator means a source, all right? So on the left here, where I say generator means a source, we have a line, which is an eighth of the wavelength. The line has a characteristic impedance of 50 ohms, has a load at the end. And we want to find the input impedance. Okay, so we'll use the Smith chart. What do we have to do? We have to normalize. We have to normalize the load, and then whatever we find is going to be normalized. And then if we want to find it in ohms, we will have to denormalize it by multiplying with 50 ohms, which is the reference impedance. Okay, we used as reference impedance. Okay, here we say used, we will use Z naught equals 50 ohms as the reference impedance. Okay, so we normalize the load, is here. Okay, 2 plus J, and now we have to find it on the Smith chart. So we draw the circle that goes through 2. You see it here. Then we draw the circle that starts at 1 for it's positive, so it starts at the upper side of the circle, so here. Then we draw the green circle, like here. And then, it's not very well done, But at the intersection of the two, that is going to give you 2 plus J. All right, that's your normalized load. Normalized with respect to 50 ohms. Okay, now what else does it say in the problem? We found that. Let's go back to the problem. What does it say? You then have to see the input impedance here, which is away from the load. The load is here, the impedance is here. So you want to find the input impedance here at a quarter, eighth of a wavelength away from the load. All right, so now we will write the circle that goes through the impedance point. And that purple circle represents the transmission line in this particular case, all right? So then we will have to move on this circle towards, there are two possibilities moving, either this way, or moving that way. However, you see here what it says, if you read that or other Smith charts, will say that this is the direction toward the generator. So this is the direction we're gonna take, this one. The other one is not good, so we'll remove this. Okay, so then we start from this point. Let's call this point A. You're gonna have also points here. We start from point A that gives you the load impedance, and we move. But how far are we gonna go? The next question. All right, so what are we going to tell us? How far are we gonna go? What is gonna tell us that is the length of the transmission line. The length of the transmission line is 8/8 of the wavelength. Okay, so now what do? We are looking at this outside perimeter of the Smith chart. Look at that. When we look at this from the beginning, it starts here at 0. All right, that is 1 point, starts at 0. It goes up, if you look 0.06, 0.07, and all of this, and these are wavelengths. It goes all the way until it comes to 0.25, and then goes all the way down until it comes back to 0.49, and then to 0.5. All right, 0.5 and 0 coincide. So having said that, if I want to remove this and this, that is 0 on one side. Oops. Okay, so that is 0 on one side and 0.5 on the other side, and all is measured in lambda. All right, so practically that tells me how to move, which means if I have to go for 1/8 of the wavelength, 1/8 of the wavelength is going to be how much? 0.125. All right, so I have to move by 0.125. So what do I do, since of course I'm starting somewhere else, I'm not starting in the beginning. So I'm drawing this line here. I'm drawing this line that you see dotted. And I'm drawing this line until I come to this point here. And then I'm reading on the outer perimeter to see. So I find 0.21 here. And then is 0.21. I put 0.21, but it's 0.212 something, or 4, 0.214 lambda. And then I need to move around as the arrows show. You see the arrows? I need to move around from this point by 0.125. So how am I going to find where I'm going to stop? I'm gonna find it here. I'm gonna add 0.214 and 0.125. And I find this number, so I have to go from here where I started until I find point, which was different, obviously, 0.339, which is kind of 0.4. So 0.4, oops, here, okay, 0.4. And then let me see something here. I need to find a better intersection. So the intersection between this circle and this line, which I will show in a different color. So here, that intersection, that's the point where I stop. So I go from A to B. Okay, that's point B. Now, this is the point that represents the impedance I'm gonna find in the beginning of the line. All right, so the beginning of the line, how much impedance I'm gonna find. And if I were to be more accurate here, because I have not been very accurate at this point, when I did that, did it fast. I have to find which of the red circles go through this point B, and practically is very close to 1. So I will put it somewhere here. Okay, so this is the red. Now you're gonna do it much more carefully than me. Do it by hand, all right? So let me see better. Anyways, there. And then I will read it here. I don't have to go very far because it's very close to 1, say it's 0.98. All right, so let's assume it's 0.95. I put it here. Say it's not exactly, I will put 0.98. Okay, and then I draw from this one, B, the green circle, which you're gonna see like this, which in fact does not have to go all the way in the beginning, but it only has to go down here so I can measure, and then I can find 0.94. Okay, I leave that. So I found an input impedance, which is 0.98 minus J, 0.94. And in fact, let me put it there. And that is the normalized input impedance in this line. And if I want to find the input, I denormalize it, which means I multiply by 50. So it's 0.98 times 50 minus J 0.94 times 50. And that gives us 49 minus J, oops, 90.94 times 50. 47. And that is in ohms. So that's how you find the impedance when you move along a line. Okay. Now, let's give us a problem similar to the one I have given you in class. All right, so now we are going to solve a problem like this. Before we go there, I need to add some other things. So let me, to remind you also, let me add a couple of pages here. Add a page, 1 probably is enough. And then I will move this. I need to remind you something else. I will remove this. Here. Okay, All right, so first of all, a quarter, we have two types of transmission lines, which I had them also in the notes that I gave you in class, or together with the homework. I gave you some notes, but there are two types of transmission lines which are very important. So transmission lines. Importance sections. Okay, so number one is a quarter of a wavelength line. All right, very important. And then what you need to remember when you have something like that in front of you is the following. You need to remember those things because, you know, they are fundamental. There are not that many. And if you know them, then you're gonna save a lot of time. So lambda over 4, Z naught, and this is the input impedance here. Let's call this, all right, A over A prime. We will always name this, as you will see, B prime. All right, and let's assume that in this one, put it a little further out. I'm gonna find the input impedance. All right, in a line like this, you need to remember that a line that does not necessarily do anything, it's not a transformer, it's like a quarter of a wavelength line, all right? I mean, we don't use it to match anything. We just give you, give you a line with Z naught, all right? Let's assume that, and I will give you numbers. Z naught is 50 ohms. And let's assume that ZL is 50 minus J50, all right? Without trying to solve this problem, you need to remember. So remember, a quarter of a wavelength line inverts its load at the input. So the input impedance of a quarter wavelength line is the inverse of the load if they're all normalized. So Z input normalized is 1 over ZL normalized, or Z input over Z naught is equal to Z naught over ZL. Okay, so these two. So a quarter of a wavelength line inverts the load, all right? So you can call that an inverter too, because it inverts the load. So a quarter of a wavelength line is in reality equal to an inverter, an impedance inverter. Impedance or admittance inverter. All right, these are things that are very important. Normally we do them in 322, but I want to remind you, you have to keep this in mind, especially now that we do design in this class. All right, the other one, other important half a wavelength line, 2. The other section is lambda over 2 line. Okay, let's see what that happens. Let me get the same so I don't do a similar design. Copy, paste. Okay, and then I make this 2. All right. Then I will also give you the numbers because we'll check this on the Smith chart to see it. Let's assume that we have the same ZL is 50 minus J 50 ohms. 50, Z naught is 50. All right, then in this case, Z input is the same with the load. So I have a wavelength line or an integer multiplier of a high half the wavelength line always transfers the load through the line. So the input impedance at the input, not everywhere in the line, so at the input of a half wavelength line, you have an input impedance which is equal to the load, both normalized and non-normalized. So Z in normalized is written like that, all right? So because we can cancel these two, what do we find? That also Z in is equal to ZL. So this is for a half a wavelength line. These are very important and you will have to remember them, all right? You should not use the Smith chart. I mean, these are, if you have it in your problem, you remember that this is happening, and then you will save yourself a lot of trouble by not trying to figure it out at that moment. And it's not difficult to remember, right? Half a wavelength transfers it, in a quarter of a wavelength inverts it. So now let me show you why that happens. We'll do it only once and then we're not gonna try to do it again. So let me see, get that here. All right, you remember those things. All right, let me then move this, put one more page. Okay, and then I will take this. Here. And then we'll try to put a Smith chart. Copy. Okay. And put it. Let me make this a little smaller. Okay, so this one here, and then let's try to put this one there. And put this one here, and then put this one under. Okay, because it's gonna break anyways. The way I'm gonna. All right, so now let's try to put here paste. All right, that's good. All right, we'll clean it up. Okay. Now let's see. How is that the case? Let's find 50 plus J50. We normalize it, all right? You remember we said that. So normalized ZL is 1 plus J minus J again, minus 1 minus J. All right, let's try to find it. I will do things fast right now, faster rather. One is here, the resistive line. All right, so let me do the circle still. No, it's so bad, do not like it. Okay. to go to 1. All right, that's 1. And then minus j is down negative, is here. The intersect right there. So here. That is ZL normalized, okay? Then I draw the circle that has a center at the center of the chart and goes through ZL. So let me see how that I'm gonna do this. Okay, goes through ZL, comes closer. There. All right. Okay, there. All right. Then I'm now taking the diameter. Okay, and I find where I have, in this particular case, I don't necessarily need it, but I don't need the diameter in this. Why do I say diameter? I need this one. Point. In fact, it interacts with this. So this point. Okay. And I can put this one here. Right. And then I see from here what number I have when if I want to read it, it's going to be 0.3. 0.33 is here. Let me see there. 0.33 is here. 0.34 is here. So that is going to be 0.338. All right. So let me erase this one and this one. Oops. That's not good. And this one. Okay. So that's 0.38 lambda. And now I have to move towards the generator like this, but I have to move for about 1/4 is 0.25, okay, lambda. So I will have to move around like this for 1/4 of a wavelength, which therefore, if I move for 1/4, so 0.338 plus 0.25 gives 885 point lambda. So I have to go around until I find 0.588 lambda. So I start, and I go around like this. Then I arrive here to 0.5, and then it stops. It goes to 0. So if I arrive to 0.5, then I have to find another 0.088. So I go for an additional 0.088 and I stop there. All right, so that is the point where I stop. And then I connect. So I was not very wrong when I did the diameter, but it was too much of a jump for you. So practically it goes there. And what does it show? It shows two things. First of all, we found the input impedance here. All right. Let me see. We found the input impedance here because we were at ZL, and then we moved by a 1/4 of a wavelength, and we came to Z in. But what is the other thing that I found? That it moved only by half a circle. So it's like moving from ZL to Z in is like I go and I use the diameter to take me from ZL to Z in. So, but we said before, if you go on this purple circle, and you go from your load ZL and use the diameter to find another impedance, that is really your admittance. All right, so practically that would have been the admittance of ZL, but the admittance of ZL is nothing else but the inverse of normalized ZL. See that? So already a quarter of a wavelength on the Smith chart, it inverts your impedance. That's exactly what we found here. You see this here, and you see here on the Smith chart, all right? So practically a quarter of a wavelength line, both on the Smith chart and on paper with the equations, it moves directly your load and makes and inverts it. All right. Now, if I were to be on a half wavelength line, which is like this one here, all right, same load, same characteristic impedance, but my line was half a wavelength. In that case, instead of moving by a quarter of a wavelength, which is this, I would have to move by half a wavelength, which would take me back to the original point, ZL. So I would have to move all the way around, and then I would come here, which in fact says exactly the same, that if I move on the Smith chart by a half a wavelength, then I write the whole Smith chart and I come to the same location, which is exactly is what we said here, that if you move along a half wavelength line, you transfer your impedance. Okay, so that's how to show it on the Smith chart. Now, with this, I think we are ready to go and start solving problems like that. Okay, and in fact, I have also, can you remind me in the homework that I gave you, one is a half a wavelength and the other is a quarter, isn't it?
Yes, ma'am, it is.
Okay, perfect. So this is like the half wavelength. All right. Now, when therefore you have a problem like this, and they ask you to find Z02, all right? So that what they are asking you to do, let me go, in fact, in this, they ask you to find Z02 and D, so that the input admittance is 10 millisiemens. So the input admittance at B is 10 millisiemens. So they ask you to find that, and they give you lambda over 2, and then they give you Z sub L is 30 minus J 300 ohms. And then next to that, you have a stub, which is open here. All right. That means open. And the stub has a length D. You don't know it, but you know the characteristic impedance, you're going to find the length D. So practically, the most important thing is to try to change the shape into something that involves two wires for the lines. I mean, we will do this for some time until we can get rid of it. We cannot get rid of it right now. So after you give this from me, then you practically have to go to this one, all right? And say, this is my problem. I have a section of line. In this case, I put, all right, so I have to put here, I gave you a little different, so I did not, it was not identical with the homework. So I put here Z02. And then this is Z01. And I gave you Z01 to be 150 ohms. And I gave you the load. I did not give you any, I just gave you that lambda, that this BC is lambda over 2. And I want you to find what I wanted you to find is the D so that the input admittance is 10 Siemens. Okay. So let's see what we have to do with that. First of all, let me, before I go, just a second, because I think I may need to go closer to your homework for a moment. So let me find your homework. I'll come back to this. So let me find your homework for a second. So, okay, Canvas. Okay, assignments. Homework. Okay, homework. All right. So this, okay, this is the ups. This is the problem. Okay, so I gave you a quarter and half. All right, let me do the half. In the half, I will change some things. I will put 100 ohms there. Let's see what we're gonna get. All right. So let me go back. I'll keep what I have. And it says, solve this problem using the Smith chart. So I'm going to this, all right? So for you, I suggest you put it in this form that is a little more familiar. Okay, and then look what I'm saying and what I'm doing here. I put here an input, Z in over A prime. And I know, if I look towards the load on this transmission line, the half wavelength line, I will find an impedance. I call that impedance the input at A prime. And then if I look towards the stub, which is open circuited, that's the red, then I see another impedance, which I call the ZS at AA prime. So that ZS is the impedance I see at AA prime as I look through towards the stub. On the stub, meaning I am on the stub, looking towards the stub, and I find this impedance, and the other one, I am in the beginning of the line, I'm looking towards the load, and I find the input at AA prime. Now, if I do that, then practically this simplifies into this form. Okay. I have two impedances in parallel, or because, I can, let me erase it here and I will rewrite it practically, but I want to erase it just to make it easier. So you can follow what I'm saying. I will write the same. So if I do what I said previously, then this one is going to be my Z in at AA prime. All right. And this one here is going to be my ZS at AA prime. All right. Now I have two impedances in parallel. However, it's easier if I change those into admittances. All right, if I change those into admittances. Why is that? Because if I have admittances in parallel, then it's the sum. The combination of the two is the sum of the two admittances. So practically it's better for me to work with admittances. Okay. So now I have, if I simplify it in this form, I have that my input admittance is YS AA prime plus Y in AA prime. Okay, and I want to use the Smith chart. All right, so now what I will do, I will erase some of these parts so we can follow. Let me erase it. I was writing this before, but I will erase it and then do this again. All right. On the basis of what we said, all right, on the basis of what we said, what is, without doing much, what is the input on the basis of what we said before? Let me write here a question. What is what is the input at AI prime? What is that? What do we know from the half wavelength line? How much is that? Who is gonna tell me? What did we say that a half wavelength line does? A half wavelength line transfers the load the way it is. So practically the input at AA prime is equal to ZL. Okay, so the load transfers. There's nothing you can do about that. It goes, therefore, and it's 30 minus J 300. Okay, and then if I want to invert it, now I take the Smith chart because it told me to do Smith chart work. All right, I don't want to do calculations. That's what it said. Oops. Why is that? Okay, move it. Move it. Okay, let me see. All right, then I will eliminate that. Okay, so I will have, then we write this. So now I will, from this one, I have to find Y in. So I'm gonna find Y in, I will have to invert it. So how much is the Z in AA prime? I don't have normalized it. And as a matter of fact, I don't even know how much Z01 is gonna be, Z02 is gonna be. So I'm going to Z01 and I use that, and nobody has told me what to use. I'm using the one characteristic impedance I know, and Z01, we said it was 150, all right? So we know that Z01 was 150. So now I'm normalizing ZL with respect to 150. And that is going to be 0.2 minus J2. Okay. Now that I have normalized it, I can find the admittance. So I'm going here, and it's 0.2 the real part. So I'm doing here the red circle, 0.2. Okay. All right, and then, and it was 2, the reactive part, and it was negative 2. And 2 is here. So look at what I'm drawing, the green line. All right, so this is, okay, this is here. Z input at AA prime, normalized with respect to 150. And then what do? I draw the purple circle that has its center, the center of the chart. And let's see who this is gonna be. I'm gonna do my best. Okay. we'll see. I don't have anything else to help me other than this. Move it a little bit. Okay. Well, close enough. And then we go, you're going to do it more carefully, obviously. And then I will draw the line from here. Okay. From here. There. And then I will get the diameter and I will find the point, which is here. All right, and that is y input at a prime. All right, and now I can read it, and then I find that y input normalized at a prime is equal to real part. It's going to be approximately done what we see here. It's going to be 0.1 here, 1, 2, 3, 1, 2, 3, 3, say 4, close to 4. I will make it approximately 0.04. Okay, 0.04. And because there are at well, let me see. No, we'll measure it up here, and then that's gonna be plus 0.5 plus 0.5 0.05. Yeah, 0.5 rather. 0.5. Yeah. Okay. Which means that if I want, well, I'll keep it the way it is. All right. So we have now found this. Oh, well, I apologize for all of these things. We have found this impedance, admittance rather, out of this equation. Okay. And we know Y in has been given to us. It's 10 millisiemens. So if we have, however, to come to in this equation, they all have to be either non-normalized or normalized. Otherwise, you cannot normalize to the same. So practically, from the original equation, we call this one. From 1, we have that y in normalized is equal to ys a prime normalized plus y in a prime normalized. Okay. Now we're going to normalize y in. How do we normalize y in? With take 10 millisiemens. 10 millisiemens. And we normalize it with respect to y01, which is y01 is the inverse of z01. Z01 is 150. So it's 10 millisiemens divided by 1 over 150. And therefore is 10 to minus 3 times 150. Okay. And is 1.5. So that's what we find. So y input normalized is 0.5, 1.5, excuse me. And that has to be equal to y s at a prime plus y in at a prime, which is ys at a prime plus what we found from normalized y in 0.04 plus, oh, there should be a j here, j.5. However, what is happening here? What is happening here is that from the theory of stubs, all right, if you have a stub which is open here, and this is Z01, and then you want to find the input. So open means YL is 0. All right, you remember the open? The open, it means that ZL is infinite, or the inverse of infinite, which is YL is 0. Okay, so if you have a stub and you go on the Smith chart, let me take now the Smith chart and check the stub there. Copy. And we put here paste. Okay. Make it a little smaller. All right. And then I will erase. If you have a stub, the stub is always the load of the stub is going to be infinite, like here for open, impedance infinite, or it's going to be 0 for short. All right, so open is either the impedance infinite or admittance 0, and for short is like either the impedance 0 and admittance infinite. But let's take that is open. So infinite impedance normalized is infinite, so it's here. It's right here. All right, and therefore, if we are to move around the stub by a distance d, then we will have to write the circle that goes through the center of the Smith chart and goes through that point. And this circle is like exactly that, goes right here. All right, it's all in the inner perimeter, which means none of these points has a real part. No matter how far we move, all right, from our load, no matter how far I move, all of the points I will find on my way, we will have 0 real part, because this is 0 real part in the impedances. Which means from the Smith chart, without even looking at equations, that if I have an open stub and this is my input of the stub, oops, let me call this A prime, and this is at A prime. So this base, according to the Smith chart, let me write it here as a matter of fact, this base at A prime normalized is gonna always be reactive. All right, always for a stub. Okay, what that means is if this is always reactive, all right, both impedance and admittance, and this has a real part, and then this has a real and an imaginary part, that with this being only reactive, that implies that only this will only impact the imaginary part, and therefore the real part, this one, in this equation, this one, and this one will never become equal. What does that mean? That means you cannot design, therefore, a circuit like this, where this is lambda over 2, where your ZL is what I gave you, and your input is 10 millisiemens. You cannot do that design. There is no, therefore, a value for ZOE or length for D that will make this possible. That's what it shows, all right? And you can see this through the Smith chart here. So in one of the circuits I gave you, that is going to be the case. In the other circuit, it's going to be a design. So in any case, I mean, or maybe I don't remember now, but I think look at the solutions the way I gave you this one, and try to follow. It happened in lambda over 2 that you could not do the design. In the other one that I gave you is lambda over 4. All right. So with lambda over 4, you remember what happens to the impedance? It becomes inverted. So the only thing you will have to do is to just find the normalize everything with respect to, let me go back to this problem. Let me go to this one. Let me see here. Okay, so let's go. The lambda over 2, we solve something similar. Let's go to lambda over 4. What you need to remember to solve lambda over 4, and then you apply the Smith chart, is that a quarter of a wavelength line, like the lambda over 4, Z01 characteristic impedance, is gonna invert the load. So you know immediately, without using anything, you know how much is gonna be the input impedance to the quarter of wavelength transmission line. And then you can set up your problem and find this is an open circuit. You can solve it for the rest to find the stub. So that's what I wanted to show you today. I think I tried to go as close to the problems as I could, all right? And I wanna stop here and see if you have any questions. I will upload the slides that I just wrote. Here, where did I did it? Yes, I will upload the slides, which is what we did this today. And then I will also upload the video, which I will do it tomorrow. And then I want to see if you have any questions for me right now.
Is there any chance you could upload as well a Smith chart for us to print off?
Which chart?
A Smith chart, just a blank one?
Yes. Yes, thank you for reminding me. I will do it right now. Yeah, I mean, I can do the slides right now and the Smith chart, but I will do the video tomorrow sometime.
Okay, and you did say you're gonna push out due date till Monday
Yes,
evening?
on Monday.
Right.
Yes, also now. All right. Okay, thank you so much. So I will do this, and yeah, you're welcome. Take care.